Okay, and welcome back. This is the Virtual Residency Workshop 2023. It's Tuesday, June 27th. It's the early afternoon session, the design and structure of a cluster supercomputer, and I'm your presenter, Henry Neeman from the University of Oklahoma. So let's dive right in. So a quick outline. We're going to talk very briefly about what is supercomputing, and then we'll get into what's a cluster supercomputer. On the what is supercomputing part, I suspect we can go very, very quickly because I think y'all probably, or at least most of you probably already know all this stuff. Then we'll go into cluster components, and then we'll break that down: nodes, network, storage, software, and the facility, why we have clusters, and then if time permits, which it probably will not, I will give an analogy for how certain kinds of parallel codes operate, but time will probably not permit. So let's dive right in. I want to start with a warning. Starting right now, from now on, you are no longer allowed to use the word cluster to mean a supercomputer. Not because you shouldn't be allowed to do that, but because all it does is create confusion. And here's what I mean by that. And instead of saying cluster, say cluster supercomputer or HPC cluster or just supercomputer, or the name of your institution's supercomputer, right? If it's named, so for example, a neighboring supercomputer is called Buddy, refer to it as Buddy. Don't call it the cluster. And here's why. The word cluster is extremely overloaded. Virtually every discipline uses the word cluster to mean something very different from what all the other disciplines use the word cluster to mean. So if you use the word cluster to mean something else again, all you're ever going to do is create confusion. So instead, you want to use an unambiguous term like HPC cluster or cluster supercomputer, because you can't expect that all the researchers you're talking to will know what you mean when you say cluster. Some of them will think you mean what they mean when they say cluster. Make yourself easy to understand, not hard to understand. Okay, so what is supercomputing? There are lots of definitions. I'm going to give you the easiest one that you can explain. You can literally explain this to a grade school kid. I know this because I've done it. Supercomputing is the biggest, fastest computing in the world right this minute, which means a supercomputer is one of the biggest, fastest computers in the world right this minute. And the reason we say right this minute is it's always changing, and in particular, it's always getting bigger and faster. So a good rule of thumb, if it's 100 times as big and fast as what you have on your lap or your desk, you could probably call it a supercomputer. And then, of course, in the world of supercomputing, we don't call supercomputing supercomputing, because if we call supercomputing supercomputing, then you might think you know what we're talking about, and we can't have that. So instead, we have lots of other jargon like high performance computing and cyber infrastructure and things of that nature. So these are all equivalent for our purposes. So what's supercomputing about? Being big and being fast, right? By big, I mean a problem that's too big to fit on your laptop, which in principle means more than a few gigabytes to a few tens of gigabytes, and or more than a few hundred to a few thousand of RAM, and then more than a few hundreds or thousands of gigabytes of disk. Anything bigger than the PC, a few to a few tens of gigabytes of RAM, a few hundred to a few thousand gigabytes of disk. If it won't fit in that, you're not going to be able to run it on your PC. And speed, if you could solve a problem in a month on your laptop, that's good. But if you could solve it in an hour on the supercomputer, that's better. Okay, so what do we use supercomputing for? I generally break this down into three categories. Here's a good joke that I use with my own students. There's two kinds of people in the world: people who split the world into two kinds of people and people who don't. There are three categories of use for supercomputing: simulation, data mining, and scientific visualization. Simulation meaning make the computer pretend to be the phenomenon of interest. Data mining, looking for needles of information or patterns in a haystack of data. So machine learning is looking for the patterns, the typical thing. Gene sequencing is looking for specific little patterns, little needles of information in a haystack of data, things along those lines. And then scientific visualization, turning your giant ocean of data into pictures, or even better, movies, or even better, video games, interactive movies of the data. Because if I give you a stack of 1 trillion numbers, you're not going to be able to make head or tail of that. But if I give you a picture or a movie or a video game that represents that 1 trillion numbers, then not only will you be able to understand it, but you'll be able to derive insight, because the purpose of computing is not numbers. The purpose of computing is insight. Okay, so this is everything important in the world of supercomputing with nothing left out, distilled down to 2 bullet points, right? The storage hierarchy and parallelism. That is the entirety of supercomputing in its essence, with nothing left out. Everything else in the world of supercomputing is just decorating these 2 issues. Okay, so the rule for the storage hierarchy is anything that's fast is expensive, and anything that's slow is cheap. If something is fast, therefore expensive, you can't afford much of it, so it ends up being small. So registers, for example, are very, very tiny. I actually have a little table coming up. Anything that's slow and therefore cheap, you can afford lots of, so it typically will be very big. Okay, so here's a table that kind of shows that. I'm not going to dig into the details of it. Again, as I say, most of us already have familiarity with this. If you don't, I can refer you to a much longer talk that or set of talks that go into a lot of detail about this. But speed, your cache is super fast. So 50,000 megabytes, 50 gigabytes per second, but terribly expensive, like $10 a megabyte. And I took 2 CPUs that were very similar and just subtracted and then divided by the difference in cache size. And I found $10-ish per megabyte is around the cost of cache. RAM, on the other hand, much slower than cache, but on the other hand, much, much, much cheaper. And so on down the line, SSD, flash, hard disk, and so on. Okay. And then parallelism. What's parallelism? It means doing multiple things at the same time. Now, probably you probably have in your life, usually young people who are watching TV while reading a book, while playing a video game, while doing their homework, while listening to music. Now, they're not literally doing all of those things in the same moment. Instead, they're time slicing. They're shifting their attention from one to the other very rapidly, but they're not literally doing each of those things all in the same moment, right? That's called concurrency, by the way. That's not parallelism. Parallelism is when you're doing the multiple things literally all in the same exact moment. That's parallelism. Okay, so then what's a cluster supercomputer? Because this is what we're going to dig into. You may have seen Pirates of the Caribbean. By this, I mean the first one, the one that's actually good. And there's this scene where they're marooned on the desert island, and they got a big bonfire, and it's nighttime, and they're drinking the rum. And Captain Jack Sparrow says, what a ship is, it's not just a keel and a hull and a deck and sails. That's what a ship needs. But what a ship is, what the black pearl really is freedom. And then he curls his mustachios and passes out. But the same principle applies to a cluster supercomputer. So a cluster supercomputer needs a bunch of small computers. When they're part of a cluster supercomputer, we call them nodes. A network, an interconnection network, or interconnect for short, that hooks those nodes together so they can talk to each other. Storage, you got to have somewhere to put the user's data, and actually some data owned by the people who run the machine as well. And then software that allows all those pieces to communicate with each other so that they can work together, right? That's what a cluster supercomputer needs. But to become a supercomputer, what has to happen is all those pieces have to believe so hard that they're one big computer that it actually comes true. And what I mean by that is that all of those pieces, or at least a big chunk of them, have to be working together on a problem much bigger than any one of them could do on its own. That's what makes it one big super computer. Okay, this was the very first cluster supercomputer we had at my institution way back in 2002. It cost almost $1 million. It had, I think it was 500-ish cores, give or take. It took up an entire row, and it was capable of about 1 trillion calculations per second, just a little bit more than 1 trillion calculations per second. Time permitting, I'm going to show you the progression of 1 trillion calculations per second over the last, I think, 30 years now, give or take. Okay. So what does a cluster supercomputer cost? Well, how much you got? If you've ever been to Las Vegas or Disney World, you've already dealt with this issue, right? Doesn't matter how much money you came in with, you leave with nothing but a smile on your face. Well, if you're leaving Disney World, it's a smile on your face. If you're leaving Vegas, I don't know. But how much it costs is however much you got. Now, how much should you actually spend on HPC at your institution? Well, part of the answer is it depends on how much research that system, that capability is going to facilitate, how much research will be supported by that capability. Because what you shouldn't be doing is you shouldn't be spending more money on the tool than on the research that's using the tool. So if you've got $1 million per year research expenditure, but you buy a $10 million supercomputer, you're fired, right? You're gone. And this takes into account both the machine and the people who are running it, the facilitators, and so on. Your total annual research computing expenditure should be at least loosely based on your institution's annual research expenditure. And I've provided a link where you can look up your institution's annual research expenditure. Not every institution in the world is listed on it, but if you are at a low research intensity institution and you don't appear on that list, the answer is it's a very small number. Okay, so a good range, again, it's a loose relationship, but a good range is your institution's research computing capability, total cost per year, should be between a fraction of a percent and a few percent of the total annual research expenditure of the institution. Okay, let's talk about what's inside the machine. And more or less from here on out, at least for a while, we're just going to be talking about things. Okay, the rest of this week is about people. This talk is going to be mostly about things. Okay, what do you find inside a cluster supercomputer? There's really 4 categories: nodes, interconnect, storage, and software. And I already mentioned that. I'm going to keep harping on it. Nodes are computers, typically server computers, but in principle, they could be PCs, or in fact, they could be cell phones if you really wanted to build a supercomputer out of cell phones. I know someone who, in the distant mists of time, built it out of PDAs, out of Palm Pilots. He built a Linux cluster supercomputer out of Palm Pilots. I don't recommend that, especially not for real life production, but you can do it. And for teaching purposes, if you wanted to build like a Raspberry Pi cluster or something, you could certainly do that. But it's a bunch of computers. And most of those, yes, in principle, you could build a cluster supercomputer out of Furbies. Again, not recommended, but you can do it. Typically, the overwhelming majority of these computers can be used for number crunching, and I'll break that down. Interconnect, that's the network or networks that connect the nodes together, and also to the storage, to the users, to the sysadmins, and so on, right? Yes, there have been cluster supercomputers built out of PlayStations and various other kinds of inexpensive off-the-shelf machines, absolutely. And then you've got storage and you've got software. So what kind of considerations should you be thinking about? What's your budget and what's your funding cycle, right? When does the money show up? That's an important consideration. And how long do you have the money? That's an important consideration when you're building a cluster supercomputer or designing one or thinking through what you're going to do. The facility, where are you going to put it? And when you put it there, what concerns are you going to have? Space, power, cooling, the world-facing network. There's lots of other issues: fire suppression, weight, How much weight is the floor going to have to handle? On and on and on. There's a million things. Your team, the labor that's going to put this thing together and maintain it and help people use it. How are your users going to use it? What are their workloads like? And there are plenty of other considerations that you have to take into account. These are just sort of the big ones, but there's other things that are going to come up as well. At my institution, for example, one of the concerns that we have is we can have quite a bit of cooling, but in order to add a new exciting kind of cooling or a lot more cooling than we already have, by the way, this also applies to power, we would have to do a 3 to 6 month upgrade project that would cost at least mid, if not high, 6 figures. So in order to do a big increase in power or cooling per rack, we would have to find someone willing to put up that money. And that's not trivial to do. And almost certainly it wouldn't be a federal research funding agency. It would have to almost certainly be internal funds. Okay, let's talk about the nodes in a cluster supercomputer. So a node is an independent computer. Again, typically a server, but it could be a PC. It could even be a handheld, but typically it's going to be a server computer. And I'll break it down into 2 categories. These categories are a little arbitrary, but they're good enough for our purposes. Compute nodes, that is nodes that will be used for number crunching by researchers, by users, and then non-compute nodes, nodes that are used for everything else. Some of them things for researchers, some of them things for sysadmins or for the system as a whole, right? So compute nodes, and I'm really going to break that down into 3 subsets. The first subset is what we normally think of as compute nodes and refer to as compute nodes in much the same way that when we say bull, we mean a bull cattle. We don't mean a bull elephant, right? If we mean a bull elephant, we say bull elephant. So compute nodes are the regular old compute nodes that are doing CPU-based number crunching. Typically, they have somewhere between as little RAM as is practical to a medium amount of RAM, but not a huge amount of RAM per node. And on most cluster supercomputers, these regular compute nodes are by far the most common kinds of compute nodes. There are exceptions. If you build a cluster that is intended, a cluster supercomputer that is intended primarily for GPU computing, you might have very few CPU nodes or perhaps none. But on most cluster supercomputers, the CPU nodes are the CPU compute nodes are the most common by far. Then you have accelerator nodes. Again, you don't have to have them, but typically most cluster supercomputers do, especially the larger ones. So these are compute nodes, but they have accelerators. So GPU cards, field programmable gate arrays, et cetera, et cetera. There are a lot of different categories of these. Again, for number crunching, some for machine learning, that's increasingly popular. Some for traditional floating point calculations, the more usual stuff that we're more accustomed to. Accelerator nodes cost more than regular compute nodes for a couple of reasons. One, you typically have to have a compute node to hold the accelerator. Now, sometimes you'll have a standalone collection of accelerators that then the compute nodes can access. But by far the most common thing these days is the accelerators sit inside of a node. That also may mean that that node, for example, has to have an unusually high a quantity of RAM. It might have to have an unusually high amount of network connectivity. It might have to have unusually strong CPUs in order to be able to properly handle the accelerators. Because they tend to be very expensive, right? You start with a compute node and then you make it more expensive. Because they tend to be much more expensive than regular compute nodes, you tend not to have very many of them. Again, there are exceptions, but that's the most common approach. And then large RAM nodes. So these wouldn't have accelerators, but they would have a huge amount of RAM and maybe a lot of cores as well for applications that can only run in shared memory, but are have very large data sets. Again, typically these are very expensive. When you get up into terabytes of data within a single compute node, you're typically looking at anywhere from high 5 figures to mid 6 figures, depending on how much RAM we're talking about. And you might have, instead of a couple of CPU chips, you might have 4 or even 8 CPU chips. So again, they're very, very expensive, so you typically don't have many of them. Okay, and then non-compute nodes. I'll sort of break that into three categories, one of which you might not have, but you need login nodes. So places where users can log in, where they're going to be editing some files, they're going to be compiling if they're building their own code, they're submitting their batch jobs and monitoring them and so on. And you typically just need a few of those, or maybe even one if it's a relatively small cluster supercomputer. Then if you're expressing your storage in a way, and we're going to talk more about storage, but if you're expressing your storage as a collection of computers with disk drives inside them, then you might have storage nodes. And then you also are going to need some collection of support nodes or management nodes to run various administrative tasks. Some of them are tasks done by system administrators, but a lot of them are tasks done by the system that the system administrators set up and monitor and fix if there are problems and so on. Probably the number one for that would be the batch scheduler. We're going to talk about that. User database, disk imaging. This means putting onto, for example, an individual compute node's disk drive, if it has one, all of the files that are supposed to be there, for example, the operating system and various executables and so on. Okay, now, this raises a question. I keep saying node, 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 node. Why do we use that term? Why are they called nodes? Well, that term comes from an area of math called graph theory. This has nothing to do with like a bar chart. That's not the graphs that mathematicians are talking about. Of course, mathematicians, like everybody else, overload terms, right? What they mean by the word group is totally different from what normal people mean by the word group. So graph theory, a graph is a collection of vertices or nodes that are connected together by edges, right? So in the case of a cluster supercomputer, the vertices are, or the nodes are the computers and the storage, for example, and the edges are the network connections so that they can talk to each other. So here on the left, we have the physical layout where there's a bunch of nodes connected to a network switch. And on the right is the graph representation where the nodes are the circles and the lines are the edges. So in this particular case, every node has a direct connection to every other node, ignoring the switch, which is what creates that topology. Topology here meaning a network layout. The people who invented cluster supercomputers were very interested in network topologies, network layouts. And so they used graphs to represent those. And the side effect of that was they started referring to the computers, the individual computers, as nodes. And that the terminology has stuck around. Okay, so compute nodes, what are some of the considerations? What kind of CPU are you going to put in there? And the first thing you got to decide is the major family of CPU. Most cluster supercomputers nowadays are x86, which is the chips you can get from Intel and AMD. And by the way, there are other vendors of x86, but those are the two big ones that most people are familiar with. Now, completely different CPU families. There's ARM, which is what you find in a lot of cell phones and tablets and so on. Now you're finding in other kinds of systems as well, including now cluster supercomputers and servers and so on. Power, which was originally a proprietary IBM CPU family. Now I believe they've open sourced it and others can manufacture them. And there are plenty of others, right? There are lots of other CPU families. If you wanted to build a cluster supercomputer out of MIPS chips, for example, you could certainly do that. Or Spark chips from Oracle. So then you have to think about, well, how many cores do I want? What clock speed? How many gigahertz do I want? What CPU family? What generation, right? Do I want the most recent generation, which is possibly the most expensive? For example, that's true right now for both Intel and AMD. Sapphire Rapids and Genoa are far more expensive than the next most recent generation, Ice Lake on the Intel side and Milan on the AMD side. A big reason being, it's not just the CPUs, it's that the newest generation uses DDR version 5 for the RAM. The next most recent version is DDR4. And there's a big upcharge in the RAM because the RAM is faster for DDR5. Okay, RAM, how much do you need? what speed, how many memory channels. So every CPU chip is associated with a collection of slots that you can stick memory sticks in. They're called DIMM sticks. You can put the memory sticks in those slots, and there's a fixed number of those slots. And there might be multiple rows, but within each row, there's a certain number of slots, and those are called memory channels. And the memory is distributed across the sticks in those memory slots. And if you can fill every slot, and if there's multiple rows of these slots, then if you can fill every slot with an equal number of sticks per row, then you get the maximum possible memory speed. So that's very attractive, right? Network, card, and cable. What network? And we're going to talk in more detail about this, but Ethernet, InfiniBand, or OmniPath, they're proprietary networks that you can buy. For regular compute nodes, really, the major goal is make each one as cheap as humanly possible, but not cheaper, right? The trade-off between price and capability, and still make sure you're making the users happy. Because the number one thing that users complain about is not how long it takes them to get their result, it's how long the job is pending in the queue before it starts running. And the reason for that, I found out several years ago, and I confirmed this with a grad student. The reason is when a grad student submits a job or a postdoc submits a job to the batch system, while the job is pending, their advisor will hold them responsible. Well, you should have submitted it sooner. But as soon as the job starts running, it's no longer their fault. It's the fault of whoever wrote the code, which is usually not the grad student or postdoc, right? So you want to balance that trade-off of the best possible speed per node versus the least possible amount of time spent waiting in the queue. And that's, I mean, it's not optimizable in the absolute sense. You make a best guess. And then the special compute nodes, accelerator nodes, and the large RAM nodes. And all of these choices are going to depend on what do your users need, how much money do you have, and what's the price performance sweet spot. So oftentimes, for example, when they release a particular chip family, there'll be a particular chip model or a few chip models that absolutely maximize your bang for the buck. And picking the right one can be a really valuable thing. And so it's a good exercise to kind of plug that information into, if you have, for example, a server configurator, and try and guesstimate what the price performance ratio would be. Okay, accelerators. So accelerators are devices that can do certain kinds of number crunching much faster than CPUs, usually a limited subset of kinds of calculations. And even if they can do general purpose, typically that takes a lot more programming labor. And if the code people want to use has not been ported to that flavor of accelerator, they might not be able to run on that accelerator at all. So again, it's a trade-off. You want to serve the people who can run on the accelerator, but not completely ignore, not poorly serve the people who cannot. And some of them simply can't. Vendors will also often provide test platforms with different chips you can benchmark the software you care about. Yes, that's exactly correct. Yes. Sometimes they will happily do that. Sometimes you have to wheedle and plead. So graphic processing units are very popular right now for machine learning. They are also capable of doing traditional floating point calculations, both single precision and double precision. But they're really more and more being optimized for machine learning calculations, for what are called tensor calculations. And they're amazingly, screamingly fast at those. Field programmable gate arrays. These are essentially chips that can be turned into the hardware you want on the fly. That's a wild oversimplification, but that kind of gives you the flavor of it. The difficulty and the reason we don't see nearly as much uptake of FPGAs is that they're much harder to write software for. And so we see a lot less writing software for FPGAs, usually just in specific disciplines. The signal processing folks like to use FPGAs quite a bit, whereas, for example, the machine learning folks, you hardly hear them talk about that. And then there are special purpose accelerators that you can get from various vendors. Usually they have proprietary technology, and what you need to do in cases like that is you need to talk to your researchers and find out, is that something of interest to them? Do they already know that they could run on them and get really good value? And we've had conversations with a number of vendors here to find out what their offerings are and whether that would be a good match for a significant subset of our researchers. So far, we haven't bought any of that, but some institutions do, and they have good reasons for doing so. But again, typically for an accelerator, you've got to do the coding in a specific way. For a limited subset of applications, there's often, and machine learning is a really good example of this, there are libraries where you can essentially write a Python wrapper or a C++ wrapper or whatever around a call to a function somebody else wrote that will do all the heavy number crunching for you, that's well optimized for that kind of number crunching. You just set up the problem and then call that routine and then do whatever post-processing you need to do with the result. And that is a much more convenient way to do those kinds of calculations. And this is one of the reasons that machine learning has really exploded, is because of things like the TensorFlow library, the PyTorch library, the Keras library, the scikit-learn library, and so on. There are a bunch of these libraries where you do the setup, whatever pre-processing, you call somebody else's function, and then you do whatever post-processing. And that is a lot easier than writing the code that actually does the heavy number crunching. Okay, then the non-compute nodes. Let's talk about login nodes, management nodes, and storage nodes. So on login nodes, you typically don't need many. On a small cluster supercomputer, it might just be one. In fact, on a small cluster supercomputer, you might have one node that is the combination of login, management, and storage, right? They might all be on a single node. And, you know, the engineer in me says you don't want to have one, because then if it goes down, nobody can do anything. But when you have a small system, it's not serving a huge number of people anyway. So if it goes down, that is disruptive, but it's not the end of the world. It's an annoyance, typically not a crisis. And so spending too much money on high reliability in that case may be counterproductive. Whereas on a large cluster supercomputer with, let's say, hundreds of compute nodes, you do want as much redundancy as you can get on these non-compute systems. The redundancy on the compute systems is you just have a lot of compute nodes. Okay, so login nodes, you just need enough to handle how many users are going to be logged in at the same time, and whatever it is they'll do. Now, one of the things that you have to do is you have to make sure that people who are on the login nodes are not doing their heavy number crunching there, because that makes the login nodes unusable for everybody else who's logged in. So we, for example, run a little process that every 5 minutes essentially looks at the CPU load. And if it sees that the CPU load is too high, it also looks at how much RAM is available. If it sees the CPU load is too high, or there's too much RAM being used, then it will send us a hate mail. And then we send the user a hate mail and say, cut it out and don't do that anymore. We're politer than that, but that's fundamentally the message. If you have multiple login nodes, you can have high availability. You can even do the thing where people log into a generic name. So for us, it's schooner.oscar.ou.edu. And that actually then goes to one of, I think in our case, 3 different login nodes. And from the user's perspective, which one they get is random. I honestly don't know whether it's random or based on load or just a round robin. I honestly don't know. But it appears to be random from the user's perspective. Then the management nodes or support nodes. This is where you run your various administrative services. There's a ton of variation on how this is done. You know, one thing we do here is we have pools for virtualization, where a lot of the administrative services we run are running inside a virtual machine or a container, rather than needing dedicated hardware for each of these services, because we have several dozen of these kinds of services that we need to run, and wasting whole servers on that would be counterproductive. So I suspect that's pretty common. And then storage nodes, as I mentioned, you're talking about nodes full of disk drives, and we'll talk a little bit more about that a little bit later on. Okay, condominium supercomputing. Some of you, your institution might do this. Some of you, maybe your institution doesn't do this. I am a huge fan of condominium supercomputing because we spend a certain number of dollars per year on hardware, but we have a limited number of dollars. We have a budget that we have to stay within. Whereas the researchers, they have whatever money they've got that they're willing to spend on this. And our experience has been that the amount of money that our researchers spend on condominium supercomputing is roughly equal to the amount that we spend on general purpose supercomputing. So they basically double the size of our machine. So in a condominium supercomputing model, you let users buy their own compute nodes, and then you incorporate those compute nodes into the centrally owned cluster supercomputer, because the labor cost of running a cluster supercomputer is not proportional to the number of compute nodes. It's not even close. The joke I've heard is that it's proportional to the square root of the number of compute nodes. So if you quadruple the size of your cluster supercomputer, that doubles the labor cost. Even that is probably an exaggeration. It's probably not even the square root. The analogy is a condominium apartment building, right? Where the condominium company owns the building as a whole, but each individual apartment is owned by the occupant or someone who then maybe sublets the apartment to someone else, right? Doesn't literally necessarily have to be the occupant. But so there's owners of the individual apartments, and then there's the owner of the building that the apartments are inside of. That's the analogy. And there are a zillion different charging models and operating models for condominium supercomputing. And they kind of run in the range from, if you buy a condominium node, then you get to decide who gets to run on it and when they get to run on it, and so on and so forth. You have, I'm not going to say 100% control over it, but 100% control over who gets to run on it. The opposite of that, the far end of the spectrum, is it gets thrown into the meat grinder with everything else, but maybe you get like some priority chits or whatever, right? Or maybe you get next to run priority when you submit it, just something along those lines. And it's, you know, this is a spectrum, and there are different institutions operating everywhere along that spectrum, right? There's no standard way for doing this. And I don't have a recommendation for what you should do, right? Or what your institution should do. There's as many different ways to do this as there are institutions, and my guess is most of them are right. Okay, let's talk about the interconnect. So what do we need the interconnect for? It's really three things: nodes talking to nodes, nodes talking to storage, and system administrators talking to hardware, which includes the storage, the nodes, the switches, and so on. And depending on your budget, your needs, your usage patterns that you see from your researchers, and so on and so forth, that could be a single network for everything. Each one of those things could run on its own dedicated network, or it could be a mix, right? That it all depends on what's right for your institution. Now, there are basically three categories of technology options, and your institution might use one of these or multiple of these. All of these is iffy. I don't know if you could use all of these, but you could certainly use multiple of these. And my institution uses multiple of these, right? So the easiest one to talk about is Ethernet. Ethernet is by far the most common network technology in the whole world, right? Everybody owns Ethernet. Ethernet, my laptop, Ethernet, my house, Ethernet. Everywhere you go, all over the world, Ethernet, Ethernet, Ethernet. And the beauty of Ethernet, because it's so common, there's two wonderful things about it. One, it's affordable. And two, it's very reliable. And the reason it's reliable is it's been tested under essentially every conceivable circumstance at every conceivable scale, right? The downside of Ethernet is that the latency, and I'll explain that in a moment, the latency is relatively high. Latency is the time it takes for the first bit of a message to show up on the other end, right? So if your latency is high, that doesn't matter for a big message. If you're sending a gigabyte, you don't care how long the first bit takes to get to the other side. But if you're sending a kilobyte, that's a huge deal, because then the latency will dominate the time cost of sending the message, right? Now, if you want low latency, which is much faster performance, you want InfiniBand or OmniPath. InfiniBand is far more common. OmniPath is a relatively recent innovation. InfiniBand is older. But we'll treat them as equivalent for purposes of this discussion. So if I say InfiniBand, just assume that I'm including OmniPath unless I get real specific. So this is a dedicated internal network, right? Same as it would be for Ethernet. I'm not talking about the world-facing part of the network right now. Dedicated internal network. There are a few non-HPC applications for InfiniBand, but not many. Financial trading is a big place where they consume a lot of InfiniBand because they're very latency sensitive. If you can beat the other financial trader by a microsecond, you can make a ton of money, right? So they're very interested in minimal latency. And this is the big advantage of InfiniBand. It's low latency, so more like 1 microsecond for the first bit to get from start to finish, from source to destination, instead of 10 microseconds on Ethernet, right? But the downside is it's very uncommon, which means that it can be expensive, although I've actually run the numbers and that's no longer really true. But more importantly, it is vastly less well tested than Ethernet. As I said, Ethernet has been tested in virtually every conceivable circumstance on zillions of machines all over the world for decades and decades. InfiniBand has been tested for decades and decades, but on a relatively modest number of machines under a relatively modest number of circumstances. So it's much more delicate than Ethernet is. It's much less robust than Ethernet is. And you have to be careful how you use it. That's much less true for Ethernet. But I did an actual dollar for dollar comparison of if I wanted 25 gigabits of aggregate bandwidth when the network is fully saturated. So on Ethernet, I'll just use native 25 gigabit Ethernet. And on InfiniBand, I'll use 100 gigabit InfiniBand, but 4-to-1 oversubscribed, which I'll explain in a little bit. It turns out that the price is very, very similar. It used to be a huge difference in price. I think it was a factor of 8 was what we were seeing. Now the price is very, very similar. So I ran the numbers and I came up with it's about a 35% upcharge to reduce your latency by a factor of 10. To me, that seems like a very reasonable deal if the scale of your cluster is big enough to justify it. Okay. And then there are also proprietary networks. Usually these are for a specific vendor's hardware. They're usually low latency. I'm not going to go into details about that. So the considerations you really need to think about, number one, how many ports, how many network ports do you want on each node? Now, if you're doing Ethernet, like 25 gig Ethernet, if there's such a thing as a 25 gig Ethernet 1-port card, I don't know. I don't think I've seen those. I'm sure somebody must sell those, but your typical vendor, the cheapest card they're going to have is 2 ports. So it's not really a decision. You don't have to use both ports, but typically both ports will be available. On InfiniBand, there is a significant upcharge to go from 1 port per card to 2 ports per card. There's an even bigger upcharge to go from 1 card to 2 cards in the same compute node or node of any kind. But the other consideration you have to take into account is how much bandwidth do I need on each of these nodes, to and from each of these nodes? Because if you don't have the use for high bandwidth, then there's not much point in paying for high bandwidth. And in particular, what you can do is you can oversubscribe, which means the network speed from the node to the first level of switch can be higher than the network speed, the aggregate network speed from the first level of switch to the top level of switch. You can have a hierarchy of switches. And that way, you get a decent worst case bandwidth, a high best case bandwidth, and a lower price. Okay. Now, when would you want to have high bandwidth? It's not probably going to not matter as much for your MPI communication. Depending on how big the messages you're sending over MPI, typically latency is going to dominate. So if 1 microsecond latency at 25 gigabits per second, that translates to a little over 3 kilobytes of data per message before you feel the bandwidth impact at all, right? On the other hand, if you're talking about communication with storage, then if it's SSD, you might be latency sensitive. If it's spinning drives, hard drives, you're probably not latency sensitive because the latency on a spinning drive is measured in milliseconds, not microseconds. And in bandwidth, again, spinning drives are much slower than SSDs. So if you've got 1,000 hard drives, 1,000 spinning drives, that's going to get you, if you're lucky, 150 gigabytes per second. Best case, right? So about 150 megabytes per second per hard drive. At 25 gigabits per second, you will saturate your disk bandwidth with 48 compute nodes writing to it, right? But if you've got 1,000 SSDs, which by the way costs a lot more, if you've got 1,000 SSDs, you're looking at 500 to 3,000 gigabytes per second. So you're going to need somewhere between 150 and 1,000 compute nodes, all pushing data at maximum speed at the full 25 gigabits in order to max out the speed of 1,000 SSDs. So here's kind of a picture of this notion of oversubscription. And by the way, of this idea of how networks are set up for supercomputers. So you'll have a switch that has a bunch of downlinks to the nodes, some number of downlinks going to the nodes. And then that switch will also have some number of uplinks going to a core. So there's a core layer at the top. There's what's called a leaf layer here. The core layer is sometimes also called the spine layer. There's a leaf layer here, top of rack switches, as they are called. And so you're downlinking to a bunch of nodes, you're uplinking to the core. And depending on how many downlinks and how many uplinks you have, that will give you your oversubscription rate, right? So here's kind of a picture of that. Here on the right is fully subscribed. So for every downlink, I have to have an uplink. That'll give me an equal amount of bandwidth going down and going up. And that'll be full subscription. So even if I fully saturate the network, I'll still be getting the maximum theoretical possible speed from node to node. If I want to reduce my cost, if I want to cut my core cost in half, then what I can do is I can have twice as many downlinks as uplinks. So in a 40-port switch, 26 downlinks, 13 uplinks gets me 2-to-1 oversubscribed. And I left one port unused. I hate wasting money. 4-to-1 oversubscribed on a 40-port switch is real easy. 32 down, 8 up, right? But that's the principle. Okay. And by the way, on this topology, notice we've got these multiple core switches. If I send a subset of the connections from the leaf switches to the core switches, a subset of those connections, then each one of these paths gives me a different way to get from this node to this node, right? So I can go from here to here, or I can go from here to there. Right. And if I've got 4 core switches, I've got 4 different paths. So if one of my core switches crashes, no big deal. I'll just switch to another path. And that all happens automatically. If one of my leaf switches crashes, I lose its compute nodes completely, but all the rest of the system continues on as if nothing had happened. Okay. And there are weird factors that can play into how much you oversubscribe. I want to make sure I don't overconsume my time. Am I already at my time? No, 1:30. Okay, I'm doing good. All right. I was a little worried. So one of the things we discovered is, particularly for InfiniBand, there is a huge disparity in price between copper cables, which are short, versus fiber cables, which are long. Now, actually, the real disparity is in the connectors on the ends of those cables. Yes, copper is a bit more expensive than fiber as a material, but actually the real issue is the passive connectors on the ends of the copper cable. Those are cheap. The active connectors on the ends of the fiber cable, those are expensive. And if you have a copper cable with active connectors, and in fact, you can get that for InfiniBand for certain cable lengths, then That's not quite as expensive as fiber, but boy, is it expensive, way more expensive not as expensive as fiber, but more expensive than passive. Okay, so here I've actually run the numbers. This is fresh, hot today, an hour ago. I looked up these numbers. If I've got an HDR splitter cable, so 200 gig on one end, a pair of 100 gig on the other, a 2-meter passive copper cable is $300. A 3-meter active copper cable, so the expensive connectors, is $1,500, and a 3-meter active fiber cable is $2,500, right? And the active copper, they only have 3 and 4 meter, if I remember correctly. So once you get beyond 4 meter, you're doing fiber anyway. So if you can, for the leaf switches, if you can get all of these connections to be copper, the reduction of total cost of the network is enormous. And so this becomes a huge consideration, because how many nodes can I fit within a 2-meter cable run of the leaf switch so that I can afford my cluster instead of not be able to afford it at all, right? Okay, let's talk about storage. What should be the top priorities of storage? There's really 4 factors that we generally consider. Reliability, because if the thing goes down, it doesn't matter. If your storage is dead, your supercomputer is dead, right? People can't do their job if they can't input their input and if they can't output their output, right? It's useless. Capacity, how big do you need? Speed, how fast does it have to be? And price, how much can you afford? The old joke was big, fast, and cheap, pick any 2. Right? If it's big and fast, it's expensive. If it's fast and cheap, it's small. If it's big and cheap, it's not fast. Okay. So what kind of hardware do we find on a cluster supercomputer? Well, there's typically sort of 3 categories. One is cheap boxes full of disk drives. And more often than not, that means either a server that has a lot of drive bays in it, or a server that's connected to a box that has a lot of drive bays, what we call a JBOD, which is short for just a bunch of disks, right? So a JBOD is an enclosure that has bays for lots of drives, and you hook it to a server, typically directly physically connected. Now, you might have something where it's a bunch of independent chunks of storage that are relatively inexpensive. Maybe they run independently, maybe they're aggregated. And then if you have a big budget, you can buy a proprietary storage system, which means it would be big, fast, reliable, but not inexpensive, not cheap. Okay. And then you've got to worry about what's the software that's going to run on top of that storage hardware. Cheap and easy is the network file system, comes built into Linux. It is slow, but it is reliable. It's like Ethernet. It's tested under every conceivable circumstance. Then there are many free and typically open source parallel file systems that you can get. So we've been running a lot of Ceph here lately. In the past, we ran Lustre. There are lots of institutions that run BGFS and OrangeFS and so on. Then there are proprietary file systems, and I've only listed a subset. So it's the software only runs on on the same vendor's hardware. So IBM has Storage Scale, formerly known as General Parallel File System. Weka has WekaFS. Isilon, which got bought out by EMC, which merged with Dell, has OneFS. Panasys has PanFS, which we used to run here. And there's lots of others. This is not by any means an exhaustive list. There's a ton of them. And then there's a hybrid where you can run hardware with open source software, but it's treated as an appliance and the manufacturer stands by it, certifies it, provides support for it, and so on. Lots of options. Now, file systems. There's lots of different file systems. Yes, another example is VAST, Cumulo, Pure Storage. God, there's a zillion of them. I don't even want to try and hit all of them, and I'm not trying. So for anybody I missed, my backward apologies. But now, What you could do is you could throw all your users' data onto one big file system and say, you sort it out. It's not really ideal. What you look for is commonalities in user behavior, how they use the storage, and then try and design toward that. So commonly, the home file system, which is where small files are typically stored. These are things like your software, your scripts, your little input files, things like that. So for example, on our home file system, we give everybody a 20 gigabyte quota limit, and then they can ask for more, but yeah, in some cases, yeah. All right. So it's not generally, home is not typically a good place to put bulk data sets, whether input or output. Home is typically backed up regularly. And I want to be careful about the word backup. And I think I have a slide about this, and I'll explain what I mean specifically by backup. But here I'm talking about a nightly incremental of everything that's new or changed since last night, and then occasionally a full dump of all files. That might be every week or every month or whatever. Scratch, on the other hand, is sort of the opposite of home. It's big, it's fast, it's shared, and it's temporary. So files are not supposed to live there forever. It is not a graveyard for people's data. Typically, Scratch file systems are not backed up. And the reason they're not backed up is backing up a very large thing is very expensive. And people don't want, institutions typically don't want to spend an enormous amount of money on backing that kind of stuff up. And I'm going to break stuff down a little bit in a minute. Do you need a parallel file system? Well, part of it depends on what your users need and want. And part of it depends on whether you've got the staff or the third-party support to be able to manage a parallel file system. They are a lot harder to work with than something like NFS, right? That can be very expensive. How big should it be? It depends on the budget. It depends on the user behavior. And do you have a purge policy? Could a node's local disk be used as Scratch? In principle or in practice? So in principle, absolutely. And in fact, we do that here. We call it local Scratch. In practice, the difficulty is what happens if a job crashes? What will become of that user's data? Do you mark that node as offline until you can copy the Scratch data off that node to some globally accessible place? Or do you try and mount the local Scratch on all the compute nodes, every local Scratch on every compute node? So you have like local Scratch 001, local Scratch 002, up to local Scratch 857. That can be an awful lot to manage. So we provide local Scratch, but the rule is when the job ends, the data disappears. So part of your batch script should be copying the output to a globally accessible file system, right? I would not recommend using the local disk drives inside the compute nodes for the globally accessible Scratch, or indeed for any globally accessible storage. You can do it. I'm just not crazy about it. And how do you prioritize for Scratch? Size versus speed versus reliability versus cost. I think a good rule of thumb is reliability has to be number one, because if it's down, you're done, right? We do use temp space at case as well as Scratch, but Scratch is recommended. The difficulty that I've seen with temp is it can be easy for users to fill it up, and other things than the user depend on /TMP. There are processes, there are operating system level processes that use /TMP. And if the user fills /TMP, then those processes can fail. So we would prefer to have a separate partition for local Scratch rather than putting stuff in /TMP. Plus, once you teach them to use /TMP on the compute nodes, they're not going to make the fine nuanced distinction of not using /TMP on the login nodes or wherever else, right? Okay, and then you can have like work or project, that's some dedicated persistent storage. Typically that has to be done in a condominium-like way, because unless your institution is very wealthy, you do not have the money for all the storage they need. And in fact, having them pay for their dedicated persistent storage is a big win, because then they minimize the use of it so that they minimize their cost. Whereas if you give it to them for free, they will use it all up like that, right? Again, we don't typically, here at my institution, we do not typically back up the work or project storage. We encourage them to archive instead, because you have to have or identify a long-term parking lot for their big data sets. Right. And I want to distinguish what I mean among these two concepts, and I'll add a third: backup, archive, mirror. So backup, as I said, nightly incremental of any file that's new or changed since last night, and then an occasional full dump, maybe weekly or monthly or whatever, of all the files. What that means is you can have multiple versions of the same file name on the destination. And so you can say, oh, the user regrets making such and so change, so we can retrieve a backup from a day before they made that change, right? Or if they delete a file, we can go back and retrieve the file they deleted. If you delete a file from the source that's being backed up, eventually that file will get deleted from the backup, but not immediately. And eventually all the versions of that file will get deleted, but not immediately. An archive is the opposite of that. It's write once, read seldom. So typically you've got to upload the files to the archive on purpose, although there are cases where that's done automatically. And a file of the same file name in the same directory, you have the most recent version only. You don't have older versions being retained. If you delete the source version of a file, that has zero impact on the archived version of the file. And in fact, if you want to delete the archived version of the file, typically you have to do that manually. You have to make a choice to delete the archived copy. You have to do it as an act of volition, right? And then a mirror is where the source and destination are identical to within a small time lag. And I'm carefully not defining small, because small could be anything from a fraction to a second to 24 hours. So I'm carefully not defining small, but there's one version of every file, both in the source and in the destination, and deleting either the source or the destination, well, actually deleting the source deletes the destination within the time lag, right? Okay. Now, the reason all the storage stuff is so super important is because the #1 cause of outages on cluster supercomputers is storage failures. And I looked at 2 different places that are dumb enough to publicly post all of their unscheduled outages. Most institutions do not publicly post that information. They'll send it to people in email, but they won't put it on their websites. But these 2 places do. One of them is Access. So I looked at it through last week. Of the, I guess it was 11 unscheduled outages that they reported, 6 of the 11, so the majority, were storage failures. And then the next biggest one were 2 failures on the ticketing system. And then everything else, there was just 1 instance of, right? So half of the outages, in this case, slightly over half of the outages, were caused by storage failures. Purdue posts their outages on their website. So I went and looked that up, and same thing. Half of the outages were caused by storage. They've had power cooling problems. So about a quarter of the outages were power and cooling, and everything else was just like 1 instance of that kind of thing. So storage is by far the most common source of failures on cluster supercomputers. And so treating your storage with that in mind, treating your storage as delicate, as fragile, is very, very important to having minimal downtime. All right, so how do you decide what to do for storage? Well, #1 is you got to figure out what's your budget. And then where are you going to put all of those files that people want to store? Do you put it all, like if you're going to have home and scratch and work or project, are you going to put all of that on one physical device or collection of physical devices? Or are you going to have separate physical subsystems for each kind of data? Or is it going to be somewhere in between? Are you going to have a mix, right? This is a spectrum, not a stair step. Different users have different usage patterns. So you've got users who are mostly doing sequential reads, right? Some bioscience codes do this. Sequential here meaning it's small numbers of very large IO transactions. So you initiate a read of an entire gigabyte. That's that's 1 IO transaction, but the individual transaction is quite large. The opposite of that is random IO. Random IO, you're doing, say, a kilobyte of read or write in a single transaction. And typically that means you're doing zillions of such transactions, right? So are you doing mostly sequential reads? Are you doing mostly sequential writes? Like computational fluid dynamics, for example, does mostly sequential writes. The way that, for example, weather codes, which are in a sense a flavor of CFD, or at least closely related. The way that a weather code works is you do 5 minutes of number crunching on each of 1,000 cores, and then all the cores stop, and they each write 100 megabytes, and they're all writing to a single file. And then after they've all written to that file, so now that file is 100 gigabytes, a single file of 100 gigabytes that was written all in one go by 1,000 processors in parallel. Then you go do another 5 minutes of number crunching, then you stop and you do another write, and so on and so on, right? Very sequential, right? Machine learning, on the other hand, is mostly random reads, right? So we've got a user who is doing each experiment, they're inputting 1 million files of 1 megabyte per file, right? So they have to input a terabyte, but it takes a lot longer to input a terabyte in 1 megabyte transactions than to input a terabyte in a single 1 terabyte transaction, okay? Or mostly random writes, right? That's another thing that happens commonly. It's really hard to optimize one single storage system to do all of those well, okay? Now, the other thing is that you want to aggregate, because disk drives are, even though they're big, they're also small, and even though they're fast, they're also slow. So what you want to do is aggregate the disk drives together. And the original way to do this was RAID, redundant array of independent disks, or inexpensive disks, you sometimes hear. And there's several different flavors of RAID. RAID 0 is striping. I take a file, I split it up into chunks of roughly equal size. I give a chunk to each of several drives, right? I've got 10 drives in my array, and each drive gets 1/10 of that file. The problem with that, the wonderful thing about that approach is I have 10 times as much capacity, and it runs 10 times as fast, right? Because I can write all those chunks in parallel. The bad part is if any one drive crashes, and drives crash all the time, if any one drive crashes, I've lost everything immediately forever, right? Can't recover. RAID 1, I have 2 drives and I mirror them, right? So if one fails, I've got a perfect copy of it on the other one, I'm good to go. On the other hand, if I lose 2 drives, I'm dead, right? RAID 10 is I will stripe across drives, but then I'll have a mirror, or maybe I'll stripe across mirrored pairs. I can never remember which one is which. Now, the problem with RAID 10, it's very reliable, it's high speed, but it's expensive per terabyte, right? Costs twice as much as RAID 0. Okay, RAID 5, on my 10 drives, 1 drive's worth of capacity will be redundant data, so that if I lose a drive, I can trivially reconstruct all my data from the remaining 9 drives, right? So there's no loss associated with losing a single drive. The problem with RAID 5 is if I drop a new drive in and I'm rebuilding to the new drive, and then another drive fails while I'm rebuilding, then I'm going to lose everything, right? And in fact, if a drive fails even before I drop another drive in, I'm going to lose everything. With large hard disks, a lot of storage folks now consider RAID 5 deprecated. Yeah, I absolutely do not recommend RAID 5 ever. We've had 2 groups on campus who were running their own RAID 5. We weren't running it. They were running their own RAID 5 and they lost everything. 2 different groups this happened to. It hasn't happened in the last 5 years because nobody does RAID 5 on our campus anymore because I tell them this story, right? RAID 6 is RAID 5, except you have 2 drives worth of redundancy. So if you lose 1 drive, it's no big deal because you still have the redundancy. And while you're rebuilding, you can lose a whole nother drive and you're still fine. But if you lose 2 drives, now you've got a problem, right? Because then while you're rebuilding, if you lose a 3rd drive, you've lost everything. And the time it takes to rebuild under RAID is roughly 1 day of rebuild time per terabyte of the capacity of each drive. So if you've got 20 terabyte drives, rebuilding from a single lost drive takes 3 weeks. The probability of a second drive failing during that time is terrible, right? Okay, so there are better solutions. ZFS, which originally came to us from what was then Sun Microsystems, now Oracle, They do a thing that's like RAID 5 called RAID Z. They do a thing like RAID 6 called RAID Z2. They do a thing that's even better than RAID 6 called RAID Z3, which is 3 drives worth of redundancy. And then erasure coding is like RAID Z3 or like RAID, except that you can decide how many drives worth of redundancy you want. Any integer number of redundancy drives is fine, right? And Ceph is an example of that. You can also, for example, GPFS offers an option, if you pay an upcharge on the license, offers an option to have erasure coding. There are others as well. Okay, and erasure coding also has the benefit that rebuild times are much, much, much shorter. Okay. So the problem with putting all of your file systems on one physical storage system is that if you lose that storage system, you've lost everything and you're down, right? And until you can get it restarted, your users are completely out of business. This is really bad if you are not a 24-hour shop, a 24/7 shop, which I suspect most of us are not. It's really bad if that happens during Christmas break. And I've run the numbers. Christmas break can be, in practice, as long as 16 2/3 days. I think it's if Christmas falls on a Wednesday, because then the holiday would be, It doesn't matter what the details are. People would take an extra couple of days off because it's just a couple of days. And then you'd be running for almost 17 days before anybody was in the shop. So we design all of our systems so that they are robust to Christmas break, to breaking on Christmas break. If, on the other hand, you put every file system on a separate physical storage system, then if you lose the home file system, then everybody's dead. If you lose Scratch, most people are dead. And maybe you don't care. If you've got a small system, that's okay, because, it's an annoyance, not a crisis if people are down for a few days. But if you can afford it, it might be better to take things like the home file system or the Scratch file system, break them up into subsets. And then if a subset goes down, that takes down a certain fraction of the users, but the system can keep operating for the users who are still up, whose storage is still up. That's more robust, even though those users experience downtime. Your supercomputer is still useful, just not to those users until you can get their storage back into production. And that's true of home and Scratch. Also, particularly with Scratch, you may find that the users are better served if there are more options available to them for different usage patterns that are designed and optimized for different usage patterns. Okay, real quick, because I'm very low on time. Software, of course, there are the user applications. Depending on the size of your institution and your annual research expenditure, you could be supporting between dozens and thousands of user application software packages. Here at OU, it's typically somewhere between 600 and 700 at my institution. At the big national centers, it's typically thousands. So I remember, this is probably now getting on to 10 years ago, the director of the Texas Advanced Computing Center at University of Texas, Austin, was giving a talk, and he said, at our national center, right? This is one of the big national NSF supercomputing centers. At our center, we support 4,000 applications. 50% of our usage is roughly 40 of those. So 50% of their usage was 1% of their software. Okay, then there's the OS. It's usually some flavor of Linux, or at least something Unix-like. The batch scheduler, there are free ones, there are proprietary ones. You can pick whatever is a good fit for your institution. Compilers, user database, provisioning system, and so on and so on and so on. There's a zillion of these, right? Okay, but this raises a question, because I mentioned the batch scheduler. Why do we do batch? Nobody likes batch. Batch is terrible. I feel about batch the way I feel about democracy and old age. It sucks, except compared to the alternative. And let's talk about what we mean. So the alternative to batch is interactive. So everybody logs onto whatever compute nodes they want and runs whatever they want, whenever they want, right? How's that going to work out? right? Because the problem is your supercomputer costs a lot of money, so it's always got to be active. It's always got to be full. Even at 4 o'clock in the morning on Christmas Day, it's still got to be full, right? The only way to do that is if everybody can run whenever they want, wherever they want, and don't have to pay attention, don't have to sit there and keep an eye on it, right? Your supercomputer has to be popular in order to pay for itself. Okay. And for any individual researcher, the only deadline in the whole universe that matters is their deadline, right? I'm going to go a few minutes over. Sorry. So scenario 1, no batch system, right? So what happens? Everybody logs in down to whatever compute nodes they want, runs whatever they want, whenever they want, right? They don't care. They don't even know that that's a problem. The problem, of course, is they're going to overload all the compute nodes. And so the system is going to be, for example, it's going to be using virtual memory, which means it's swapping everybody in and out of disk. It's thrashing. It's not getting any benefit out of the CPU cache because it's thrashing the cache. It's thrashing the RAM. It's thrashing the disk. Everything is going nuts. It's running terribly slow, and more likely than not, things will crash. Okay. So now everybody's furious. So they're going to send hate mail to me as the center director. And we don't have a batch system. There's nothing I can do about that. So eventually they get tired of sending hate mail to me because I don't do anything about it. So they send it to my boss. My boss gets this giant pile of hate mail. And, you know, as a boss, if all I ever get about somebody is hate mail, they must suck. So I'm going to fire them, right? So I get fired, right? I must suck. Okay. Am I going to let that happen? Of course not. I've got mouths to feed. So what am I going to do? Okay, well, what I'm going to do is don't run. I'm not going to let you run on the compute nodes. Send me a description. You send it literally to me, and I'll use my calendar, Outlook, or whatever to schedule you on a particular set of nodes at a particular time, and that's when you get to run your job, right? Of course, you've got a deadline coming up, and the only deadline in the universe that matters to you is your deadline. So you're going to ask, oh, you know, I got this paper coming due next week. Can you bump me up in the priority queue? But of course, everybody's going to ask that all the time, which means I have to tell most people no most of the time, which means they're angry. So they send me a hate mail. I can't do anything about it. So they send a hate mail to my boss, and again, I'm fired. I'm not going to let that happen either. So I need someone who can do the calendaring without people getting mad at them. And the only person who can do the calendaring without anybody getting mad at them is the machine, a piece of software called a batch scheduler. So we don't do batch because we love batch. We do batch because the alternative is we're all fired. Now, how many users do you need in order to justify having a batch system? The reality, and this has been proven empirically, including in front of me, 2. Yes, thank you, Horst. 2 people. If you have 2 users on a system, you need a batch scheduler because inevitably they will fight over it. They won't mean to. It's not that they dislike each other. It's just that that's inevitable, right? Okay. I'm basically out of time, so I'm going to stop there. I won't go into the facility thing. We don't have time for any of that. So I'm going to leave that there, but you have the slides. There's lots of additional material in the slides. And real quick, I'll take a few questions, but I want to leave time for the break before Melissa's talk. Okay, copper versus fiber. How often do these setups or parts of these setups need to be replaced? Does this impact long-term costs in a substantive way, going with copper versus fiber? So we've got copper equipment that's been in production since 2015 and is still going strong. And the failure rate on it is very, very low, which is good because it's not trivial to replace those components anymore. That doesn't seem to be a big deal. What you really have to worry more about is at what point does a particular version of InfiniBand or OmniPath become obsolete, where it's no longer supported by the manufacturer, where you can no longer get driver updates, things like that. That, I think, is a much bigger consideration. The probability of cables failing, or even the cards, even after a significant lifetime, the failure rates are still pretty manageable. With Ethernet switches getting faster at 100 gig and even 400 gig, is InfiniBand still worth it? Yeah, what you're paying for in InfiniBand, and you saw my numbers on that, right? There was about a 35% upcharge to go from the same bandwidth when the network is fully saturated on Ethernet to the same bandwidth on InfiniBand when fully saturated, which means a factor of 10 or 10-ish improvement on latency for a 35% upcharge. Yes, it's totally worth it because MPI in particular, but also random IO, IOPS, are going to be governed typically substantially more by latency than by bandwidth. So yeah, it's wonderful. I mean, so InfiniBand now has NDR, although I don't know if you can get the switches yet in general availability. You can get the cards and I think the cables now. But NDR is up to 400 gigabits per second per port on the cards and 800 gigabits per second per port on the switches. And XDR is probably not that many years away. So InfiniBand is not having difficulty keeping up with Ethernet bandwidth. The real consideration, I think, is how much upcharge are you willing to endure to get a huge improvement in latency? And our experience has been it's totally worth it. Okay, based on your experience, what is the minimum size of storage a successful HPC needs to support researchers? I think that's an unanswerable question because you have to ask a lot of other questions to get the answer to that question. The question is, how much storage do your researchers need to be productive? And there's a lot of sub-questions associated with that, like the difference between how much high performance storage they need, for example, Scratch, versus how much archival storage they need, which could be cheap disk or it could be tape. But you have to look at what's your budget and then what do your researchers really need? And remember, if you spend all your budget on storage, that's exactly the same as not having a supercomputer at all. You've got to balance what you spend on compute against what you spend on storage and what you spend on interconnect. You've got to, that doesn't mean it's 1/3 each by any means. It has to be based on what you anticipate your researchers are likely to need. I know that was a non-answer, but the reality is that the correct answer to that question is always going to be, it depends. More questions? All right, then real quick preview of coming attractions coming up at 1:15. Is that right? Melissa Cragen will be doing the cyber infrastructure landscape organizations. And I think that's going to be a fantastic talk. So stay logged in and we will shortly be back. So it's going to be, I think it's 18 minutes or something. Something like that. 22 minutes, something like whatever it is. 1:15. We'll be back here with Melissa to do her talk. So talk to you soon. See you soon.